Okay, everybody, this is some supplementary slides about functions and derivatives. This is the first in a series of four slides, sets of slides and videos that will cover the calculus that is necessary for this course, intermediate micro theory. So first, you're probably wondering why calculus. Well, in this class, and in economics in general, we're going to look to help describe an individual or a business's optimal decision. And that requires describing how total benefits and total costs change for a small change in activity. So for consumers, how much will consuming another unit increase one's utility? For businesses, how much will selling another unit increase revenue? And how much will selling that same unit increase costs? And that is, we need to mathematically find out where marginal benefits equal marginal costs. And so you should recognize this as the optimal decision rule for both consumers, businesses. And so how we get to that is we take the derivatives of the total cost or total utility or total revenue functions. And that gives us the marginal utility or marginal revenue and marginal cost. And so in this course, I make the calculus purposefully as basic as is humanly possible to still uh, help describe and fulfill the learning outcomes. And so I like this quote by John von Neumann, who is one of the inventors of game theory, which is a really important discipline and tool used in economics. In mathematics, you don't understand things, you just get used to them. And actually, for me, this about approximates my relationship with calculus as well. So I took calculus in high school and I did really poorly on like the first and second tests. And I had like a C, and it was the first class I had ever had a C in high school in. Uh, but I started to pick it up and I just kind of got used to calculus. And so it's more than just a method to torture you. And so I just want to address, why am I using a textbook with calculus applications, given that calculus isn't even a prereq for this course. So the book has more in-depth calculus applications than we use in this class, but how that helps is because when they want to help, the book wants to help you through those applications, it has a really in-depth appendix. And this calculus appendix is awesome. It's really thorough. It's really short and precise. And these slides try to translate it into really basic English, provide examples and some practical advice, and then help you kind of fit it into economics as well. So any calculus question you're having trouble with, you can start with the appendix in the book and then also use these slides. And so the calculus not being a official prereq, that's why I make it as bare bones minimum. Unfortunately, I can't completely get rid of calculus because it does feed into one of the expected learning outcomes. And so that makes it really hard to teach this class. And so these slides and the textbook choice represent my best attempt at compromise to help you learn those learning outcomes without uh, requiring you to be a math major who's fantastic at calculus. So what I'm going to cover, um, I'm going to cover functions and functions of several variables, which you would not have seen if you haven't taken Calc 3 yet. And then I'm going to start to describe the intuition behind derivatives in these slides. And then in the next slides, I'll start talking about rules and partial derivatives and finding the extreme of functions. And while I don't have a lot of memes in this set of slides, I will go pretty heavy on the memes in the next slides. And so I have this guy who says, I wish I had a functional relationship, and it's a vertical line. And so we want to talk about functions a little bit. So, what does a function do? A function you've seen probably since at least high school math. And a function associates each member of a set X, or our independent variable, in science terms with a single member of another set Y, which is our dependent variable. And so, uh, in other words, how do you know if something is a function? Well, an easy way to kind of understand what is a function and what is not is to look at one graphically. And so we know that if a mapping of x coordinates to y coordinates fails of the vertical line test, then it is not a function. And so over on the right side, over here with our functions, I have an example of a function and not a function. And so first we notice with our function, all of these vertical light blue lines, they only touch the function once. And so we know that this mapping of x to y, this y equals x, mapping is a function because these vertical lines only touch it once. Each vertical line only touches the function once. Now we know that this is not a function here because this same blue vertical line touches the blue function at least twice. Or touches it twice at least one time. So if I were to draw a bunch of other vertical lines, these would also touch it twice. And so we can say that this is not a function because it fails the vertical line test. And so it's kind of an important place to start to know that you understand functions and what they are and what they're not. And so we're going to be working with these functions where we all know we know that they all pass the vertical line test. Okay, and so building on a function of one variable, y equals x, now we need to talk about functions of multiple variables because that's what we'll be doing in this course to understand trade-offs. So while it's graphically convenient, there's no reason that y cannot depend on multiple variables. So um, maybe just best to start out with what a three-dimensional space would look like, right? And so in the top one, we have a three-dimensional coordinates where you're used to this x and y plane, but now there's also this kind of height, and that's the z variable. And so a point in this space is described by 3 points, right? So our y coordinate, our x coordinate, and our z coordinate lead us to our point in three-dimensional space. And so you can see here that there's like an xz plane, there's an xy plane, and then there's a yz plane. So it's 3 dimensions. We're not just limited to our 2 dimensions, height and or width and length anymore. Now we also have a height dimension. And so we can begin to describe things in 3-dimensional space. And it's not going to be extraordinarily important for us to completely understand these 3-dimensional planes in this course, but just note that this 3 dimensions is how engineers and other disciplines are going to start to model objects like cubes, spheres, and other things, and use calculus to help us understand those things in 3-dimensional space. But what I want to draw the analogy to is something that's more relevant for social sciences, and something like that would be body mass index. So this is something that everyone should be familiar with. Body mass index is a function of 2 variables. It depends on both weight and your height. And so it's some function of weight and height. So now we have 3 variables where the kind of the z, what your BMI is, depends on both your weight and your height. And so if BMI is z and height is x and weight is y, then we can write your BMI z as some function of x and y, and we know that the BMI formula is weight over height squared. And so this is really close to utility, for example, depending on both your consumption of good 1 and good 2. And so that's why I kind of wanted to start here so we could see the parallels. And so now we need to start talking about the intuition of a derivative. And I started to get here with the utility slides. I think that's week 6, day 2. And so some of this is going to look a little bit similar. And basically, derivatives are building on our concept of slope. And so while slope is defined between 2 points, we can have a derivative, which is just the slope at only 1 point. And so derivatives are summarizing how a function changes as its arguments change. And so some 2 examples would be y as a function of x, or z as a function of x and y, where the things inside, or the variables inside this function are its arguments. And so this is from the Perloff textbook that you have in figure A2. And so I'm going to start to describe this figure with these slides. So one of the ways to describe how a function changes as its arguments change is via the slope. So the graphing slides have a more in-depth discussion on this, which I've already posted, or you can kind of look over here where slope is the rise over run between x1 and x2. And however, what we need to get towards is a way to describe the slope at just one particular point. And so while we have our slope formula up here, derivatives are going to kind of build on the slope formula. So y2 minus 1 is x2 over x2 minus x1, or rise over run. Another way to write the rise is f of x over 2 minus f of x over 1. Remember, because our f is a mapping of just x to one particular y, and so 1 is equivalent to the slope formula. And so this equation 1 here depends on both x1 and x2, but we want it to depend on just one x, so just like an x1, for instance. And so what we can do is define the difference between x1 and x2 as h. So x2 equals x1 plus h, as you can see here, and it's also written over here on the y-axis, or the f of x axis, in the Perloff textbook. And so then we can sub in this x plus 1 over h for x, and we get f of x1 plus h minus f of x1 over h. And then what we do is we make this h infinitely small, and so then we have just the top being just f of x1 minus f of x1. And that's what we get our derivative, and that's kind of described more in this text right here. But I'll also show you what I did in the utility again. So basically we start with h being kind of very large, and we get this linear approximation, which is a1, but that's not the same as the slope just at this orange point. So what we do is we pick points even closer to this orange point, and now we have something that's even closer to the slope just at a2. And then once we get h all the way down to 0, then we've got our tangent line. And the slope of the tangent line is the slope of the utility or function here just at this exact point. And so we have the derivative of a function at any point is, and this is the formal definition of a derivative, the change in f of x given a small change in x equals the limit as h goes to 0, so as h gets infinitely small, of this expression here. So you probably saw this in Calc 1 and were tortured slightly with the idea of what a limit is. And so this essentially gets us the tangent line in this picture. We actually won't need the kind of formal definition of a derivative, which relies on limits in this course very much, so you don't have to worry about that. But it is helpful to know that as h goes to 0, this gives us our derivative. Now, if we want to equate marginal benefits and marginal costs so that we have the optimal decision rule, we need the derivative at each point on the entire function, not just at one point. And so we need h to go to 0 at every single point on this function, which is a lot of different points. And that's where the derivative rules come in handy. And so with our derivative rules, we can get, we can kind of get away from just this h as h goes to 0, or as the difference between x1 and x2 kind of gets infinitely small, and we can have the total utility function and the marginal utility function, where this marginal utility function just describes the slope of this utility function on every single point on the utility function. And so I just want to give you a less economic and a more generic example. But as I said, like the function in the bottom graph just shows the slope of the top graph at every single point. And so if I did this without like a utility function, I just had some f of x, we have f of x equals negative x plus 5 squared minus or plus 25 in the top function. And so you can see it's this parabola because it's an x squared, and it's just kind of shifted over and up. And so we have it's downward sloping all the way until it gets to x equals 5. And then at x equals 5, the slope is 0. And then after x equals 5, it's positive sloping again. And so you should relate that really closely to the graph on the bottom, where the slope of y we can see is negative, but it's getting less negative until we get to 5. And then right at 5, the slope is 0, right? The slope is 0 here too. And then once we get above 5, the slope is positive again. And so that's why it's positive and getting more steep, positively steep here. And so this graph on the bottom, you can get from the graph on the top if you know the equation of the function using derivative rules, which is what I'm going to talk about next. And then with that, we can begin to talk about how much additional utility or how much additional cost consuming or producing another unit will be. And that's how we get to the optimal rules for calculus or for an individual or a business. So that's what we're going to talk about next is these derivative rules, which we're going to use um, in this upcoming slides. And I just want to briefly say here, so I got some extra resources that I went and found for you. There's a lot of other things. So many other economists who use calculus more regularly and more sophisticated than I have put out guides. They're probably better, more complete. My slides are just trying to do few things very well in basic language, which is like as simple as possible. So you can go to these books. OpenStack's Appendix A will have some formulas and equations, single variable calculus, multivariable calculus. The book skip volume 2 because Calc 2 is mostly torture with difficult integrals and limits and other miscellaneous torture. I have PTSD and flashbacks just thinking about it. And then there's some other miscellaneous web resources. So Khan Academy is pretty basic. There's a really basic derivatives rules here. And then these guys are really good economists at very good places. And these reviews are tailored to be more in depth than what I'll provide in these slides. Anyway, I'll be back with the derivative rules that I promised in the next set of slides. Thank you.